Okay, so what should we do right now is stop for a while. Let's take a detour. The detour is basically to justify the theory given by de Broglie. I basically want an experimental proof which gives me an idea of matter waves. That is, wave can sometimes behave as matter and matter can sometimes behave as waves. And they do it all the time. That's the duality, that's the symmetry in the nature. So I want some evidence, I want some experimental proof regarding it. So then comes the duo of Davisson and Germer. So these two guys, they designed an experiment which gave me a clear evidence of duality of matter. So let's find out what was the design of the experiment, what were the results of the experiments, and what were the implications of it. So let's get going. Now let's shift our attention to Davisson-Germer experiment. Now Davisson-Germer experiment is actually an experiment which proved de Broglie's idea of matter waves as correct, or that's a very consolidated proof of de Broglie's idea, to be precise. So as photoelectric effect consolidated that light behaves as matter, Young's double slit experiment consolidated that light behaves as a wave. Davisson-Germer experiment consolidated that matters sometimes behaves as wave. Right? So it's direct proof or direct experimental proof of de Broglie's idea. So let's look out what is Davisson-Germer experiment. So this is a brief timeline. Before we start off, we can look at the timeline over here. 1924, de Broglie came up with his idea. 1927, Davisson-Germer experimented on that idea, created an experiment and proved it was right. A couple of years down the line, he got the Nobel Prize. That's how the scientific society works. You come up with an idea, someone gets interested, he or she proves your idea to be correct, then you become famous and you get the Nobel Prize. Now, let's talk about the experiment right now. So I have electron gun, which you can see over here. So electron gun will throw in accelerated electrons which were accelerated in the electron gun or in a tunnel, and then were thrown out with a particular speed. So it's a high energy electron which comes and hit the nickel crystal. Now after hitting the nickel crystal, they get scattered. Now obviously there is no one particular direction of scattering, they get scattered in different directions. Different direction being different angles, right? They can get scattered in different angles. So if I told you this idea, that is, I'm going to do an experiment where I will be throwing on small balls on a board and the ball will get scattered, what comment can you give me about that scattering of the balls, small balls? You will end up seeing that these small balls will get equally scattered in different directions. As there is no preferred direction, you throw the ball, it gets scattered in a different direction. So every angle or every direction is equally favored or is unbiased. What we witnessed when doing this experiment, now imagine electrons to be small balls and nickel crystal to be the wall. So when we did this experiment using nickel crystal and electrons, what we witnessed is a particular angle was favored. Now that was a bit of a shady thing for me. Why? Because I was expecting equal intensity at every angle, but I got an angle which was favored. Now the reason behind this, that is the conclusion which we were able to draw, is that electrons were behaving as waves. Now how are electrons behaving as waves? For this you need to get inside nickel crystal. What exactly is happening with the nickel crystal? So nickel crystal, I have this nickel atom over here, and there's another nickel atom, and there's another nickel atom. So this is a layer. So there is a layer of nickel atoms. Similarly, there is another layer. Then comes the third layer. So this layer goes on and on and on. Now when I consider electrons as waves, what happens is the wave comes in, it's reflected and goes in this direction. Then the other wave comes in, hits and goes in this direction. Right? the path difference, what they have, the path difference, this is the separation between these two is d. That is, the separation between two nickel atoms is d, and if the angle formed is, let's say, theta, whatever, let's say I call this one, so I will get the path difference between these two light rays, or these two waves, these two waves will be d sine theta. The path difference. Now, according to path difference, I know when there is a particular path difference, there will be a phase difference, and when the waves meet with a particular phase difference, they interfere with each other. So there might be constructive interference, there might be destructive interference, or it might be a normal interference. Okay. So the reason behind a particular angle being favored in Davisson-Germer experiment is the fact that there, at that particular angle, constructive interference was taking place. So that's the reason behind a particular angle being favored. So according to the theory, de Broglie said, if you have a momentum, you're going to have a wave associated with it with a particular wavelength. So the wavelength of that particular matter wave is 1.67 angstrom. That was a wavelength predicted by de Broglie's idea. Now the experiment what we did is d sine theta is a path difference, and I equated it to n lambda. So d sine theta, the path difference, is equal to n lambda for constructive interference. And considering n to be 1, I got lambda to be 1.65 angstrom, which is close to what de Broglie predicted in the first place. So I got the whole idea that electron being a matter, we all know it's a matter, but still it has some wave-like characteristics. This proved that what de Broglie said is correct. So what we're going to do right now, we will go through the different facts about Davisson-Germer experiment. What is the setup, what were the results which we actually got, that is the raw data itself, and how we interpreted it. So we are going to study everything. So a beam is emitted by the electron gun, which is made to fall on the nickel crystal, that I have already explained you that, and the scattered beam is received by a detector which can be rotated at any angle. Now the energy of the incident beam of electrons can be varied by changing the applied voltage. Obviously, if you change the voltage, then the acceleration increases, and if the acceleration increases, the velocity will increase, so they're thrown out with a higher speed. So it was found that 50 degrees was the favored angle. That is, at an angle of 50 degrees, the intensity was pretty good, when the accelerating voltage was 54 volt. Now, based on this, I can find out what is the angle theta over there. So theta, I got this to be 65 degrees. Using this theta and separation of this, I will end up getting lambda. Now, this is actual raw data which Davisson-Germer actually did for different voltages. So its intensity at 44 volts, then I will have intensity of the incident beam at 48 volts, then comes 54 volt. This is the we picked this data up because it clearly showed a favor in scattering at a particular angle. It's 50 degrees. Now, incident at 64 volt, again this is the data which we got. According to de Broglie's hypothesis, the wavelength associated with you moving with a particular momentum should be this. How we end up getting this is E times V, potential energy, is equal to kinetic energy. So multiply and divide by M, you will end up getting EV half P square by M. So simply rearranging the term, we will end up getting 2MEV as the momentum, and simply substitute it over here. So this is the wavelength associated with you moving with a particular momentum when the particle has been accelerated through a potential difference. Simply substituting the values of constant, mass of electrons, charge of electron, Planck's constant, we can simplify the term to be lambda equals to 12.27 angstrom divided by root v. Now again, what I'm going to do is test those values, that is according to de Broglie's, I will substitute the value of V is equal to 54 volts over here and end up getting 1.67, which is in fact close to what we got using that d sine theta is equal to n lambda. So we got a lambda corresponding to that, and we got lambda corresponding to de Broglie's idea. So we have successfully compared both of them, and what I observed is de Broglie idea actually stand tall against this different notions going around. How can matter be wave and matter itself simultaneously? So these all notions were completely shattered, and de Broglie's idea wasn't for a long stay. So this is the experiment which made sure that de Broglie's idea stayed.
Now let's have a look at Davisson-Germer experiment. In this particular experiment, we witnessed, or let's say it's a proof of de Broglie's idea. De Broglie's idea being the duality of the matter. That is, a matter sometimes behaves as a wave, and wave sometimes behaves as a matter. That is one and the same thing. Each entity in this particular world, this particular universe, has a nature of being a matter and also being a wave. Now this was a very bold idea stated by de Broglie in the early 20th century, and which was considered to be a bit of absurd, because at that particular time there was a quarrel between the particle, or let's say substances being matter or substances being totally wave. So this experiment sort of settled that particular debate, that is, you can be a wave, you can be a matter. So this is a very simple experiment, as we discussed in the earlier slides. So this is just a demonstration of it. So I have atoms placed like this, and these are the atoms which are very close to each other. So if I actually throw out electrons from this particular area like this, I expect a simple rebound. That is, electrons were ejected at different angles, and each angle was unbiased, or let's say none of them were actually favored. So I have got equal intensity and all directions. Now I can play along with the size of the atom over here. So if I decrease the size of the atom and consider the same experiments, please have a particular observation about these dark spots, right? If I'm decreasing it, you will end up seeing great amount of dark spots. It means I end up getting, that is, white denotes the electron. So these are the angles at which I'm getting electrons. These are the favored directions. You can see these are the white, this is the white zone over here, and there are some dark bands also. So it means these directions are not at all favored. This is a pure characteristic of an object or an entity behaving like a wave. So this property will become more evident if I sort of decrease the size this way. You can see these unfavored directions are clearly visible over here. Now again, with the decrease or increase of atomic atom separation, I can also increase the quality of those favored direction and unfavored directions. So again, you can see, so this is a bit blurred, so let me increase the separation to 1 nanometer. Now in 1 nanometer you can see, as I've decreased, there is the atom separation has increased, so most of them will get scattered, but I will end up getting a beautiful dark band over here. This is actually the favored condition for us. So you can clearly see that being electron, I'm ejecting electrons out of it, and they are showing, and I know electrons is showing a matter, a nature of matter. We know it has a definite mass, but here in front of us, performing a little experiment, it is actually showing a wave-like nature. This phenomena, why there is a favored direction, this or unfavored direction of this and this, or a particular entity of this, or this direction being a favored angle, is because of the direct consequence of Bragg's law. So Bragg's law actually states the favored angle. That is, this angle is a favored angle, this angle is not so favored, this angle is favored, this angle is not so favored, again this angle is favored. The Bragg law was previously described only for wave, but this particular experiment clearly shows us the fact that in case of electron also I can apply Bragg's law if I am performing this experiment, hence proving that there is a duality of light or matter, or let's say de Broglie's idea stands correct.
So this is the diffraction pattern which we got at a particular voltage, diffraction or the scattering one, and here you can also see at different 3000 electrons, and here it's 100 electrons. So its intensity versus the anode V, potential V which we are giving, or let's say it's root V. That's the potential which I am talking about. Now, this is the graph. You can clearly see that some angles are favored. That is, the scattering is biased for a particular angle. So again, so this is what we got at different angles. You can clearly see that intensity rises, then falls, then rises, then falls. That is, particular angles are indeed favored.
While going through the lecture, if you face any doubt, you can post your doubt for free at askIITians.com. In order to do so, you first need to navigate to the askIITians.com. Then, while going to that link, you can use discussion board link, which is over here. Clicking on this particular discussion board link, it will take you to a page where under the head of Ask the Experts, you can post your doubt under various categories. And the team of Ask IITians Expert will get back to you between 24 to 48 hours. Now I do have a clear-cut proof that sometimes matter behaves as wave and sometimes waves behave as matter. So as to speak, Davisson-Germer experiment clearly showed us that. Now it gives me the total proof. So there is an idea, there is an experiment, and the experiment proves the idea or supports the idea. Now, for a general human being, according to the things which we observe around the universe and the nature, this is sort of challenging, or let's say contradicts the common sense of ours. So it will be pretty hard to digest. In fact, that's how come a substance be of two kinds, not simultaneously, but let's say I have two shades of me. So that's pretty hard to digest, but you have to walk this through because that's how the nature works. Sometimes it's easy for our common sense to understand, sometimes it's not. That's a part and parcel of the game. 10 years or 100 years down the line, this idea may seem to be so obvious that they may find us, the present generation, to be a bunch of fools. So you don't know what's going to happen. So right now it's not obvious to you, but it's obvious to others. So let's move forward and get on with the perfect road set up for the progress in modern physics. The detour is done. Let's figure out what to do next.